Welcome to Spontaneous Processes and Entropy. So suppose we've got some box and it contains some substances. Some blue ones, some red ones. In this case, it happens to be orange. So the system, which is the container, the box, and its contents, so our substances. The surroundings are everything outside the box. So everything outside the system. Everything else in the universe. Me, you, the board, your computer, the internet, all the computers that make up the internet. And the universe is everything. Everything in existence. All of the other stuff, the surroundings, plus the system. So the system plus the surroundings make up everything that's the universe. And this is because the surroundings are defined as everything in the universe except the system. So the two of them together have to be the universe. So the universe is equal to the system plus the surroundings. So system is the box and what it contains. Surroundings are everything out here. And the universe is all of it. So chemical thermodynamics is concerned with energy relationships and chemical reactions. The energy contained in the box, essentially. So let's consider enthalpy. We also will consider entropy in our reaction. So the first law of thermodynamics is that energy is conserved. And we can say that this way. So delta E is equal to Q plus W, where delta E is the change in internal energy of our system. Q is the heat absorbed by the system from the surroundings, and W is the work done on the system by the surroundings. And these definitions are very specific, and I've said them in that way for very specific reasons. So any process that occurs without outside intervention is what we call a spontaneous process. It just happens. And so when two eggs are dropped, they will spontaneously break, unless you happen to be really lucky. The reverse reaction, two eggs leaping up into your hand and unbreaking themselves with their shells back intact, is not spontaneous. That's a non-spontaneous reaction. So we can then conclude that a spontaneous process has a direction. A spontaneous process goes forward. A non-spontaneous process goes in reverse. So a process that is spontaneous in one direction is non-spontaneous in the opposite direction. So by non-spontaneous here, we need to draw a distinction between not spontaneous and non-spontaneous. Non-spontaneous is also directional. But if we have a process that is spontaneous in this direction, it will be non-spontaneous in that direction. Which means that if we're attempting to get it to go that way, if we have products and we want them to form reactants, they won't. They will in fact go the opposite direction. The reverse of a non-spontaneous reaction is spontaneous. This is not the same thing as not spontaneous. Not spontaneous may be non-spontaneous, or it may be that it won't go either direction. It's at equilibrium. So temperature can also affect the spontaneity of a process. So now let's get to reversible and irreversible processes. A reversible process is one that can go back and forth between states along the same path. This along the same path is important. If we can't get a process to go backwards along that same path, then it's not reversible. We can often reverse a spontaneous process, but we usually can't do it along the same path. In fact, if it's a spontaneous process, we can't do it along the same path. So, the path taken, the reverse process here restores our system to its original state. And the path taken back to the original state has to be exactly the reverse of the forward process if our process is reversible. This means that there's no net change in our system or the surroundings when the cycle is completed, because we've gone one direction on the path and then we've gone back exactly the opposite direction along that same path. If we take a different path, we aren't necessarily back in the same place for the surroundings. The system may be back in the same place, but the surroundings may not be. So, a completely reversible process is one that is too slow to be attained in practice. which means really that any process that actually occurs is not a reversible process. It is essentially an irreversible process. An irreversible process means one that can't be reversed along that same path. You may be able to reverse the direction, but you're doing so along a separate path, a different path that you had originally. So let's look at the interconversion of ice and water at 1 atmosphere at 0 degrees C. We have ice, solid water, plus heat. That will then give us some liquid water. In this case, ice and water can be in equilibrium. And if we go this direction, we're removing some heat. We're reacting away the heat to break some of those intermolecular forces between the water molecules in the ice and when we form the liquid water. If we then add some heat to the system from our surroundings, then we can melt 1 mole of ice to form 1 mole of liquid water, and the heat absorbed by the system, remember that's the way that we're defining Q, heat absorbed by the system, not heat released by the system. Heat absorbed by the system is equal to delta H fusion, so this is the enthalpy of fusion here. If we then want to go back to our original state, we can reverse the procedure and remove the same amount of heat from our system, and basically the system is releasing the heat to the surroundings are absorbing the heat then. In this case, Q is still heat absorbed by the system. The heat absorbed by the system is now a negative value because it's actually being released by the system. Right? So this is why I'm saying that there's a very specific way that we're defining Q and W. Q is heat that's defined as heat absorbed by the system. If the system is releasing heat, then that Q value has to be negative. So here we'll have negative delta H fusion, negative enthalpy of fusion. So an irreversible process is one that can't be reversed to restore the system and surroundings back to their original state. This is important. The system and the surroundings. You can get the system back to its original state in an irreversible process, but you can't get both the system and the surroundings back to their original states if you try to reverse an irreversible process. This means that a different path with different values of Q and W have to be taken to get the system back to its original state, but that then changes the energy of the surroundings, and that makes it an irreversible process. So let's look at a gas in a cylinder with a piston. So over here we've got a vacuum, here we've got our gas, and we've got some movable partition in between. So we're going to remove the partition. Right? So between here and there, we remove that partition, and of course our gas molecules are going to stream over and occupy all of the available volume. So now the gas molecules occupy all of that volume. But the piston was already out there, which means that no PV work is done on the surroundings because the volume of the surroundings isn't changing. So the work done is 0 in this case. And now we're going to use the piston to compress our gas molecules back so our system occupies the same volume that it did before we changed things originally. In this case, the surroundings have to do work on the system because the volume of the system is decreasing. Right? The system is being compressed. As the system gets compressed, in order to compress the system, we have to do work on it. What's doing work? The surroundings, something outside the system. Right? Maybe it's me or you, or maybe it's the air around us. But the surroundings are doing work on the system. If the surroundings are doing work on the system, then the value of W, the work done on the system, is greater than 0. It's got to be positive. Work is being done on the system. Energy is being put into the system. So, work is going in. This means that a different path was required to get the system back to its original state. Because we started out going from here to there, work was 0. Going from here to there, work was positive. Those are 2 different states. If here the work was negative, and there the work was positive, or in both cases they were 0, then we'd be going back along the same path, if that value for work was the same. But here, we're not. So this means that the surroundings are not returned to their original conditions. In order to get from here back to there, we have to lower the energy of the surroundings. So as we go from here to there, the system's energy is the same, but the surroundings energy decreased because we did work on the system. So we didn't get back to our original state for both the system and the surroundings. But the system got back to its original state, but not the surroundings. So that was an irreversible process. So for a system at equilibrium, reactants and products can interconvert reversibly. For a spontaneous process, the path between the reactants and products is irreversible. That doesn't mean we can't go backwards, but it means we can't get back to our original state of the system and the surroundings. We may be able to get back to the original state of the system, but in order to do so, we remove some energy from the surroundings. So this means that systems not in equilibrium undergo irreversible changes. So if any chemical reaction happens, which means there's a net change, that means it's a spontaneous reaction. It's not at equilibrium. If it's at equilibrium, then we can have reversible changes. But if there's actually any net change over time, then we have irreversible conditions and we can't get back to our original state of system and surroundings. So let's consider the expansion of an ideal gas. So we've got some initial state. We've got two 1 liter flasks, A and B, connected by our closed stopcock here. One flask is evacuated, A, and the other flask, B, contains 1 atmosphere of gas, right? Gas at 1 atmosphere of pressure. So when we open that stopcock, what's going to happen? Well, we know that some of our gas molecules from flask B are going to pass through that valve and go into flask A. That will happen until the pressure in each one is the same, half an atmosphere if the volumes are the same. And also note here that we're maintaining the system at a constant temperature. So, again, our initial state was an ideal gas confined to cylinder, kept at constant temperature in a water bath. This process is isothermal. By isothermal, we mean iso means same, thermal means temperature, so isothermal means a process or system that's kept at constant temperature. We're not allowing the temperature to change, which means that we may have to be putting in or removing heat in order to keep that temperature constant. So, the change in energy, delta E, is always equal to 0 for an isothermal process, which means that Q, the heat absorbed, is equal to negative W. So, if work is done on the system, then the value of work is positive, and the value of Q must be negative. The system must release energy by heat into the surroundings. So, what we've done here is we've allowed the gas to expand from volume 1 to volume 2, and pressure decreases from pressure 1 to pressure 2. The final state then is our 2 flasks connected by an open stopcock. Each flask contains gas at half an atmosphere. Our gas does no work in expanding from here to there, because it's not expanding against any pressure. Remember that work done for pressure volume, for gas expansion or compression sorts of things, the pressure involved is the pressure being expanded against. So the pressure that the surroundings are exerting on the system. In this case, the pressure here is 0. So this gas in B, in flask B, is expanding against a pressure of 0. If it's expanding against a pressure of 0, it doesn't matter what the volume change is, the work done is 0. So, no work is done. If it's isothermal, that means that no heat is transferred. So then, why does the gas expand? Why is this process spontaneous? And why is the reverse process, why do we not get this gas to go back into that flask? Why is that reverse process non-spontaneous? When the gas molecules spread out from our 1 liter system into our 2 liter system, there's an increase in our randomness or disorder of the system. And it turns out the processes in which the disorder or entropy of our system increases, these processes tend to be spontaneous. So, we started out, we had all of our molecules on this half of our system and none of them over there. And after we open it up, we have half of our molecules here and half of our molecules there. They're randomly distributed. Which molecules are where is entirely random. We know that about half of them are here and about half of them are there. But in this case now we have more randomness. We have more entropy than we had in that case. And it turns out that processes that increase the entropy tend to be spontaneous. So that was spontaneous processes and entropy.